2 minutes more, I will start the program.
Yes. You're a bad light here, huh?
Yeah, very well. Bom dia, boa tarde, boa noite aos internautas que nos acompanham neste programa Nanotecnologia do Avesso. Hoje, no seu número 451. Fazemos este programa dedicado ao público não especialista, porque é este público que paga as pesquisas sobre nanotecnologia realizadas no Brasil. Também fazemos este programa porque é aqui que nós podemos discutir os impactos da nanotecnologia na sociedade, no meio ambiente, na economia, na saúde, coisa que não são discutidas aonde se faz nanotecnologia no Brasil. Por fim, fazemos este programa porque acreditamos que ser livre é ser bem informado e a divulgação científica contribui e colabora para o aprofundamento da democracia e da cidadania no Brasil. Hoje, conforme tínhamos anunciado, já estamos conectados com o professor Duschi, diretamente da Universidade de Salzburg, na cidade de Salzburg, na Áustria, com quem nós vamos ter a possibilidade de discutir as questões relativas a nanopartículas e o sistema imunológico. Eu vou passar a palavra a ele, ele vai se apresentar e depois começar a expor sobre esse tema. Ok, Dr. Albert, could you please introduce yourself?
Certainly, yes. Good day to all of you. It is evening in Austria. I have studied biology at the University in Gießen in Germany and received my PhD there in 1986. I went as a postdoctoral researcher to the United States and was for 3 years at the University of California in Irvine, and then again as a postdoctoral researcher at the Max Planck Institute for Biochemistry in Munich. I moved to Würzburg, which is in northern Bavaria in Germany, was university assistant for 10 years and started there really working with particles. And in early 2001, I received the position of the chair of biochemistry at the University of Salzburg in Austria. I am at present also acting head of the university's excellence cluster in allergy, cancer, and bio-nano. So today I think we will focus on the bio-nano aspect. I have originally worked with the immune system in order to understand mechanisms of allergy. And in the 90s, there was a discussion whether diesel exhaust particles can induce allergy or make it more likely that somebody gets an allergy. I got into this, and not very much came out of that discussion, I must say. However, I got moved in the direction of particles. So since then, I have worked about nanoparticles, engineered nanoparticles, and the immune system. And the major angles that I am personally working on is safety of nanoparticles and safety of nanotechnology. We have been doing this for quite a while in a number of projects that have been funded and are still funded by the European Union under its framework programs for research and technology, and I would very much like to acknowledge the European Union for supporting this important research. I think there are several good reasons why nanoparticles and the immune system is a good match. One of them is that the immune system is evolved to protect the body from changes to its homeostasis that could be detrimental. So it's not just pathogens. Pathogens, of course, bacteria, viruses, parasites, everybody knows about that. But the immune system is also doing something against toxins, against irritants, and wound healing is a function of your immune system as well. Now, the key ability of the immune system to achieve this must be twofold. One thing is the immune system needs to be able to distinguish between self and non-self. You need to recognize your own body. You can sometimes react against your own body, but only if it has become an unnatural self, which can be, for example, mean there is virus-infected cells. You reject the cells in your upper airways when you have a cold because they are infected with influenza virus. And another case where you react against self, and it is quite proper, is tumors. The immune system can do something against tumors and quite often does so. The second thing that the immune system needs to recognize is danger. If there is no danger to your body, why is change bad? I mean, sure, a lot of things happen in your environment, but most things in life are harmless. Some are toxic, but most are harmless. Your food is not toxic, and your clothes are not dangerous, and kisses from your partner are non-self, but nevertheless nothing to fight against. So the immune system recognizes self, non-self, and it recognizes danger. It recognizes danger with a very simple trick. Essentially, your cells can die in a regulated way. They can commit suicide, package themselves into sort of trash bags, which can be removed by eating cells, and you recirculate the materials that was in them. It happens all the time. The shortest lived cell in the body is an immune cell in your blood, which has a lifetime of 16 hours. So you recircle that all the time. What should not happen is that a cell is simply physically destroyed, just killed, which happens when you cut yourself by mechanical force, or you burn yourself, or a virus is eating into your cells. In that case, you have a violent death, and material is released from inside of the cell, and the immune system recognizes that this is present. So when the immune system is able to recognize non-self and to recognize danger, this is essentially what nanosafety research is also trying to do. The professionals from the immune system have well-established mechanisms how to do this, and they do a real risk assessment, so they take into account both hazard and exposure. The response against one bacterium is very different to a response against 10 million bacteria. So there are numerous ways how to make use of these properties. One of them is certainly in safety, and I will say a few words later on about what we are doing in this context ourselves, because we can check whether immune cells do recognize nanoparticles as dangerous. There are quite general responses that go on. In particular, they go into a state of cell stress, and cell stress is a fixed program when the cell is under stress. This is not the same as if your body is under stress when you are under stress, when you have to do an examination or your favorite football team is on the brink of losing, you may be in stress, okay? But this is not cell stress. Cells undergo stress when they're exposed to toxins. For example, you inhale polluted air and cells in your airways go into cell stress. And it's possible to measure that. One area where nanoparticles and the immune system is also quite obvious is medicine. There is the field of nanomedicine, which is essentially always how nanoparticles can be applied for therapy of disease or for diagnosis. And there is now quite a number of nano agents already in the clinic, around 100 worldwide, and the number is projected to increase quite quickly. The immune system is, for many of these drugs, a good target. It's a good target because it actively tries to recognize something. So if you want to be recognized as a nanoparticle, it's quite easy to be recognized by an immune cell, and nano engineers have many tricks how to do this together with nanobiologists, nanomedical people. So it's good for directing a nanoparticle specifically to specific cells. And if you want the nanoparticle, fine. If you don't want them, it could be a good idea to attach a drug that you want to bring specifically to a certain tissue or a certain cell type. And this is indeed what is done a lot. The most frequent application of nanomedicine at this moment is cancer therapy. And when you are dealing with cancer, the immune system plays a strong role. And it's quite complicated. Essentially, the immune system can protect your body against cancer. It can recognize tumor cells as unnatural cells and destroy them, essentially stimulating them to commit suicide. This is the reverse of the suicide helpline, like saying, wouldn't suicide be a solution? Yes, it's all very hopeless. I think you should do it. This is essentially what immune cells do with the tumor cell, and an excellent idea it is. Another feature, however, is that the immune system mediates wound healing, as I said. And the tumor has real problems with getting enough oxygen and enough nutrients. It's not a well-organized organ. The blood vessels are not well developed. I should say it's a tumor. If immune functions for wound healing can be stimulated, the immune system will provide the tumor with nice blood vessels, with a nice supply of food and nutrients and everything. So it's one of the key issues in modern therapy of tumor to cut off the supply and shut off essentially the immune system doing this. So both activation of the immune system and suppression of the immune system can be beneficial for tumor. Both is also used. There's quite a number of uses in medicine for chronic inflammation. You can here downregulate the inflammation using nanodrugs, and this is in particular important for diseases in autoimmunity. For example, a disease like morbus Crohn, a chronic autoinflammatory inflammation in the gut is medicated today also with a nanodrug. And a natural thing to do with the immune system is to suppress the immune system as it is. Immunosuppressants, they are quite well known from transplantation. If you receive a transplant, you need an immunosuppressant drug, because otherwise your immune system will recognize this organ, of course, as non-self, will reject it, and you lose the organ and the transplant has failed. So such immunosuppressants are needed for many cases. There are other situations where they are necessary. If people have chronic inflammations, you may need them. If people have extensive burns, they are needed because the immune system would react against all these burned proteins in your tissue, and you would get a potentially deadly immune response beside of being seriously burned. So immunosuppressants is a big issue, and immunosuppressants in nanoform can deliver a higher dose of the drug than if you just take it as a normal pill or something. If it's just the diluted normal molecules, if they are forming a nanoparticle, you reach a higher drug load, a higher drug level in your tissue. If we are looking at the immune system in general, there are 4 ways how the immune system can respond. All of them interesting for nanoparticle and the interaction. The simplest way, also the standard, the default of the immune system is tolerance. Tolerance does not mean that the immune system does not recognize the non-self. It rather means it recognizes it, but it actively decides for tolerance. It decides not to do anything against it and to maintain this tolerance in the future, which is why you achieve tolerance against things that show up in your body. For example, when you go into puberty, a lot of proteins are produced in the body that have never been produced before. Why don't you start an immune reaction against it itself? Well, there are no danger signals, there are no wounds in the body, and tolerance is induced. You tolerate the bacteria that cover your skin, you tolerate the huge number of bacteria that live in your gut, and this tolerance is certainly important. When we are looking at nanoparticles and tolerance, it's relevant to see whether tolerance can be broken or whether tolerance is maintained in presence of nanoparticles. If it's maintained, it's a good indicator that the particles don't do anything detrimental. If you do an immune response, you go into a program to defend yourself, and this program is inflammation. Inflammation is characterized, usually can observe it very well if it's close to body surfaces, by swelling, reddening. There is heat. If you carefully touch such an inflamed site, it is warmer than the rest of the skin, and there's pain. And all these responses are good. All these responses are done by your body. Inflammation is the program how your body defends itself. It's not done by the evil pathogens. So all of that stuff is good. For example, the swelling and reddening, this means that immune cells are now migrating out of blood to the site of infection to deal with this. The heat means you heat. You can increase your body temperature. Even if there's a more serious infection, you get fever, and it's only a few degrees. But for many bacteria and also for many viruses, the temperature range where they are comfortable and where they can live is very narrow. So if you go out of that, a virus may fall apart, a bacterium may stop growing, and you can tolerate it. You are much bigger. So this is all part of the inflammatory program. This inflammatory program is relatively unspecific. So you do the same thing for quite a number of different challenges, for pathogens, for irritants, for toxin. And of course, you can also do it against nanoparticles. If there is anything in a nanoparticle that is disturbing the homeostasis of the body, that potentially can threaten its integrity, you do an inflammation. It's the same program as if it would be a bacterium or a virus. So it's very easily measurable. And the question is, will it be able to deal with nanoparticles if the nanoparticles should be dangerous. Depends, of course, on the nanoparticle and on the exact situation. Nanoparticles will not usually be impressed by increased temperature. They can be eaten by invading immune cells, but if the immune cell has eaten up, has swallowed a nanoparticle, what to do with it? If it can be digested, yes, something happens. But if you have a very stable type of particle, it will just be released again at some point and you have it again in the body. So the tools of the immune system to deal with potentially negative nanoparticles are not really very good. The essential task of the immune system is to avoid that your body is overgrown by bacteria, viruses, parasites. And this does not happen for nanoparticles. A nanoparticle doesn't divide and turn into 2 and then 4 and 8 and 16 like a bacterium would do. So the tools are not really very good. But since the inflammatory process, the nanoparticles interact with each other, this is a prime opportunity both for medical intervention, when you want to do something with inflammation, maybe you want more inflammation to fight against bacteria, maybe you want less because you have an autoimmune disease. You can do something here in the direction of medicine. Or if you're looking in safety, inflammation goes up quickly. It's a continuation of the cell stress programs that I have mentioned previously. And it's quite reliable and it's a rather fixed program. So you can look for certain markers, certain parameters, certain proteins that are produced. And if you find them, yes, there is inflammation. So this is it. Very good for safety assessments. Specific case is the so-called type 2 response. There is a type 1 response where more specific responses of the immune system come into play, building on inflammation. New tools are entering into the fight, and particular antibodies, which can detect very specific molecules, very specific structures, and then help mediate defensive activities. This type 1 response you can essentially treat together with inflammation. It's a logical continuation. You are just throwing in more different methods to handle the same threats. Type 1 is a very good decision when you have a bacterial infection or when you have a virus infection. The type 2 response is something quite different. It is involving very different molecules, very different cells, very specific, and its natural function is supposed to be the defense against parasites. When modern humans migrated out of Africa some 80 or 90,000 years ago, you can guess that they all had parasites. Until a couple of thousand years ago, everybody had parasites. If you don't have any parasites, this is an artifact of modern lifestyle, of hygiene, of medicine, of preventing parasitosis. And doing something against parasites, this is a special job. For example, parasites can be really huge. They can be big, large worms or something. Absolutely no comparison with bacteria that are tiny. And they can live in your body for a long time. I mean, there are parasites that live in a body for decades. Maybe you just want to tolerate them if they don't do so much to you. But if you want to defeat them, if you want to destroy your parasites, you need really, really hard methods. I mean, this is the immunological equivalent of the atomic bombs that you are using to eliminate a large worm. Now, you cannot, as far as we know, become allergic to nanoparticles. However, you can, of course, become allergic to a lot of plant or animal-derived proteins. So you should be familiar with it. I mean, Brazil is a country with a very high incidence of allergy, especially in the region around Sao Paulo. We have one of the highest allergy rates in the world, going up to 35% of the people affected. It's not well known why this is the case. But it's a problem. It's a general health problem. And nanoparticles could play a role here. So some things about what we are doing. This allergy stuff. I mean, we are coming out of allergy research, molecular mechanisms of allergy, what happens in the body when the immune system makes a decision to treat this particular protein as an allergen, or treat it as if it would be part of a parasite. So go with this type 2 response as a nuclear option. We have investigated this, and we have investigated the safety of nanoparticles. So it's quite natural that a couple of years ago we combined the two and asked the question, and what happens if you are exposed to nanoparticles and to allergens at the same time? The pathway that interests us, where we are working on, is inhalation. Inhalation is the major pathway for exposure to allergens, if you think about animal hair or plant pollen. And it's also the major pathway for exposure to engineered nanoparticles in an unintentional way. In an intentional way, it can be quite different. If you apply a cream containing nanoparticles to your skin, it can be quite a lot, but it's intentional, you know what you're doing. But when you inhale nanoparticles, it's unintentional in many cases. If you think about workplace, your chance of being exposed to engineered nanoparticles in air is really mainly in the workplace. And more and more workplaces do involve nanomaterials. Manufacture of nanomaterials is really just a fraction here. It's mostly use of nanomaterials. And if they can get into air, you can inhale them, which may be totally harmless, but it's something unusual and needs to be taken care of. You can inhale allergens. What happens? Is this worse than inhaling just the allergen, or is a nanoparticle with allergen attached more of a problem? We have been asking this question. Now, the allergens are proteins, and proteins attach very quickly to nanoparticles. You just add them together, and the nanoparticles are decorated with proteins. This is called a protein corona, and this is what we have when we are in the body. You don't have actually nanoparticles, you have bio-nano complexes. Now, we did this with different allergens, and depending on the allergens got different results. We had a gross allergen that did not do anything, so it was not impressed by binding to the nanoparticle. We had an allergen which was a birch pollen allergen. Birch pollen is the most frequent allergen eliciting allergy in Austria. So we know a lot about it. And it depended on the patient. Some patients responded stronger, and some the same, some weaker to allergen bound to nanoparticle. You may ask yourself, how can you test this with a patient? You cannot make people inhale nanoparticles, which were in this case gold particles, coated with allergens. No, we cannot. I mean, this would not be warranted, it would not be ethical. But what we can get is we can get blood from allergy patients. And we can measure in the blood, directly in the patient blood, how the allergic reaction occurs. Because there is immune cells specific for the allergic reactions in blood, and we can see how strongly they react. So we get a good insight into whether binding to nanoparticles makes the allergen more aggressive or maybe less aggressive. And for birch pollen, we found both. We found for house dust mite allergens that it always goes up, so it always becomes more aggressive. And there's a second feature about the major house dust mite allergen. This is European house dust mite. The official name is DERP1 if you want to look it up. DERP1 is also an enzyme. It is a protease which cleaves proteins. That is one reason why it's a particularly aggressive and dangerous allergen. It attacks proteins in the epithelia of the airways, and in this way penetrates deeper into the tissue, which means there's a stronger allergic reaction that can develop. And we can test the enzyme activity, and it also goes up. And this is starting to look that we really need to investigate this further for safety reasons, because now we are looking at an allergen, and from allergens you need very small traces to elicit a reaction. You know that if you're allergic, and certainly you know people who are allergic, they are exposed to tiny doses and they go into an allergic reaction. And we have an enzyme, which is the same protein in this case. Enzymes are also able to work at a very low dose because they catalyze one reaction after the other, so very quickly. You don't need a lot of it. And if it's more active, coated to a particle, I think we should look this up. And in fact, this is a research that is ongoing in my group, and that we are also planning to pursue for the next couple of years at least. There is a number of questions to be answered about this one. By the way, allergens plus nanoparticles, of course, there's another perspective. When you are allergic, there is only one therapy at this point, which is actually able to cure the disease. It doesn't always work, but one therapy can do it. All other therapies, all these sprays and so on that you are getting, they are only good against symptoms, but you still remain allergic. The one therapy is a specific immunotherapy, also called hyposensitization or desensibilization, where you receive increasing doses, very high doses of your specific allergens. They are injected. And this doesn't work so well, better for some allergens than for others. And people don't like these injections. 60 injections over 3 years, this is normal. And many people don't go through a whole course. They don't see an effect, and it's very bothersome, and they don't like injections. And it's also not an injection where you just go to a clinic, get a shot and walk off. You have been just injected with specific allergens that you are sensitive against. So they can't let you go. They have to keep you for a couple of hours. It wouldn't look good if you walk out of a clinic and fall dead because you have an allergic shock. It's bad advertising. So it's not a very good therapy. But if you coat allergens to nanoparticles, you could get a very high dose. And you could potentially do this by inhalation. And 60 times inhaling is probably better than 60 times injecting. So there is an interest in the medical field. There is another aspect of our own work that I would like to briefly cover, the safety assessment. The immune system should be able to recognize all threats to the body. It has to be unspecific. And we are using this feature to set up tests for essentially all nanoparticles. People from nanotechnology fields ask me, so which nanoparticles can you work with? And I say, all of them. Send me what you have and we can test them. Because we are looking at unspecific reactions, at the inflammation, we are looking at early inflammation, and there it's really, it doesn't matter whether you have silica or silver, it doesn't matter whether you have zinc oxide or carbon nanotubes. For early inflammation, we can measure that. And you want to measure it in the earliest possible way and in the simplest possible way. Because at some point, we have to go out of the laboratory. This is a real challenge in the field at this moment. We have beautiful tests in laboratories, not only in mine, in many laboratories in the world which have developed very different assays, which are using assays. So that works nicely. But they usually work with very clean, very well characterized nanoparticles. People are very proud of their nice nanoparticles. And they're highly sophisticated tests. They really have fine instrumentation, expensive equipment. Nobody in the world can do what they are doing, which gives you fantastic papers. And it's great science, indeed, but it's not applied science, because you cannot apply this outside of the specific lab. Sometimes you even have problems bringing it to a different laboratory. And if you want to do, let's say, measurements in a factory, you can probably forget it. So what we need for nanosafety assessment with biological means in real life is simple tests. The tests need to be robust, which means if it's a mixture of particles, it needs to work. If particles are only one part of what's present, if there is other stuff, chemicals, dust, whatever, gases, it also should work. If your particles are contaminated with something, and they usually are, your method should work. And this is a challenge. And it shouldn't be so expensive. So what you want is something that works with pretty much standard equipment that can easily be obtained, that is not so expensive, and the tests can be run with not too high training. I mean, if you need to work for a couple of years before you can actually operate the machine, this is useless. If you can learn it in 2 weeks, that would be fine. If you just follow the instructions, it would be ideal. So simple, robust, cheap, and able to operate outside of a research laboratory. And this is a challenge of the field, and we are trying to address this. Our most robust tests that we are having, the ones that I'm having the highest hopes for, is human lung cells. Those are lung cells derived from a tumor. Those are immortal, and we can get as many of the cells as we want. They grow cheaply and reliably. They are epithelial cells, so they form a wide layer. And if they are threatened, or if the immune system works, and they are sensitive in an immunological way, so epithelia are body barriers, so you better be able to watch out. And we can see how they respond. And we can grow those cells in a simple cell culture, which I'm very fond of, simple and cheap. If this is not sufficient, we can also grow it in air-liquid interface, meaning at one side you have a medium, and on the other side of the cells you have air, so you can mimic inhalation. We are, after all, dealing with lung here. And in order to measure in the most simple way what happens, we have produced these cells as reporter cells. A reporter cell means a cell may produce a particular indicator of inflammation. Good. Now we change the cell, so it's still producing this indicator of inflammation, which is fine. But when it does so, the cell is forced to produce a second protein at the same time. And this is a reporter protein, one that is chosen to be easily measurable. We are using three different reporter genes. They have different advantages. One is able to produce fluorescent light, incredibly sensitive, but a bit more effort to measure. One is giving you without any particular chemical reaction or so a green fluorescence. It's a famous green fluorescent protein. You might have heard about it. And another reporter is a red fluorescent protein. So you get red cells. You can, in principle, so even use different cells with different reporters at the same time. The good thing is you can measure this fluorescence anytime. What do you need? You need an UV lamp to stimulate fluorescence, and you need a camera to record it. And you are done. And if you come back in an hour, you can do it again and see how it changes over time, because the procedure does not require that you destroy the cells. You don't even manipulate them. Essentially, if you push a button, you can do it. If you manage to push a button and the thing is set, you can handle that equipment. We have also constructed a nice little device that is able to bring nanoparticles with an extremely high efficiency to these cell layers that we are testing. Essentially, they all go down from gas phase to it. We are using an electrical field to pull it down and some specific tricks to make this particularly effective. It's a box, looks like half a shoebox, and we have applied for the patent. So wish us good luck that we get the patent and can continue to work on this device and further improve it. This would be something that we have in mind, that you get a simple small device, you set it up somewhere, you read out what you want to measure, and you get immediate data on what's happening in the gas phase. Such a test would not be specific for nanoparticles. But when you are thinking about safety in the workplace, there is no need why you want to be specific for nanoparticles. If something else is dangerous in the gas phase, you want to know about it. So what would be done for nano safety improvement in the workplace here is, under normal working conditions, these cells shouldn't do anything except for control cells, which are always active. We have those too. So no matter what you do, they always go up. It just shows that the system works and that the procedure is active. And this should always be the case. And when one day one of these green or red fluorescences goes up, you need somebody to look into it, and this will then be a case where the normal safety procedures in the workplace step in, an alarm has been raised, and somebody can look. It may be that somewhere nanoparticles are escaping from a production process. It could also be that in the room next door the walls have been painted and there is no chemicals which are dangerous to health. But even if it's the chemicals from wall paint, you do want to know about it. Yes, so those are some words about nanoparticles and the immune system and what we are doing in this direction. If you happen to be in Porto Alegre next week, there will be the Toxi Latin conference, a Latin American conference for toxicology, and I will be there giving a talk on that matter.
Yes.
So thank you very much. Back to you.
Okay. First of all, I will not be in Porto Alegre, but our colleague, the name is Arline Arcuri. She will be there, and she will try to find you there.
Yeah, very good. I'm looking ahead to it.
Okay. Your talk was very complete. So many important points, and I don't have enough knowledge to put some in-deep questions. So I will put some general questions. Okay? The first question is about nanotoxicology. And my question is if the theoretical framework of the toxicology you can use for the nanotoxicology.
To a large extent, yes. So nanotoxicology is toxicology as applied to nanoparticles, and many of the concepts, of course, can be used. Many assays, however, have to be modified or don't work at all. Many assays work, for example, with light. In our case, intentionally, but many traditional assays use it too. Now you have particles. Particles can scatter light. So your readings can be a real problem. You need to change the assays for practical reasons. But there's one aspect that is truly novel for nanotoxicology, which is that concentration is essentially not particularly relevant. And we all, I mean, me as a life scientist, everybody in chemistry, everybody anywhere, grows up scientifically with the knowledge that concentration matters. But concentration in this case would be the concentration of the chemical that makes up the nanoparticle. This is not sufficient information to deal with nanoparticles, and it is not even the most relevant one. You want to know the number of particles, you want to know the size distribution of particles, you want to know the surface area of nanoparticles. That is probably the most important information. You need to know the surface properties, so what are functional groups in the surface, what is the electrical charge, the theta potential, what is the hydrophobicity of the surface, which biological components will it bind once it is in the body, which is very variable. How will it interact with cells? It becomes very difficult. And this is not necessary for toxicology, because you have a chemical, and a chemical has a chemical concentration, gram per liter or something. And gram per liter is not a useful concept for nanoparticles. So the discussion becomes more complex.
Okay.
But otherwise, it's of course anchored in general toxicology.
Okay. My second question is about the regulation. I think nanobio, we need some or more regulation than exists today. Or here in Brazil, there is no regulation about this. And I saw same thing about the regulation in Europe, or another kind, if he can put in this way, kind of regulation in the USA.
Yes.
I would like to see your opinion about this regulation and the nanoparticles in an immunological system.
I don't think it is important to have a completely new regulation, but to adapt existing regulations so the properties of nanoparticles are specifically taken into account. For cases where this is important, this is certainly useful. Europe has a regulation, the REACH regulation for chemicals, and this is now modified to include specific nano aspects for nanomaterials. So it's just a modification of an existing regulation. You don't have to start new. I mean, many of the things that we encounter with nanoparticles are, well, not unexpected. I mean, if you have nanoparticles, it's dust. It's a fine dust, but it's dust. And you do have regulations about the dust load in the workplace. You have anti-dust measures you need to take and so on. And this also works for nanoparticles. Or if you have a particle which is composed of a toxic material and it can fall apart, you have something like zinc oxide or cobalt oxide, for example, you will have metal toxicity because cobalt is toxic. Yeah. But you can base this on metal toxicity, which is very well known. There are situations where you want to do more about it, where you want to indeed make a specific amendment to regulate materials in nanoforms, and we will have to see how this is really handled in the political process. I think the scientific foundations are there. At this moment, there are more than 30,000 scientific papers in the literature about nanotoxicology. So we can't say we don't know anything. We know a lot, really. And what the regulators make out of it, we shall see. There is strong discussions about some specific regulations here in Europe, for example. It is presently a strong push to declare titanium dioxide to be a carcinogenic material. And I have doubts that this is justified. It's based on very old data that today you could never even do on rat studies that would never be permitted today. So not all regulation is automatically really adequate, but I hope that this will be a process where scientists and regulators interact and we achieve over time a really good and solid and reasonable regulatory framework.
Okay, the next question is about if you can talk for us about the balance between the promise and the realization in the development of nanobiotechnology.
Nanobiotechnology, yes. The nanobiotechnology has its biggest promise, of course, in medicine. Okay?
Okay.
Here's the biggest market, here's the biggest unmet need, and here nanoparticles really can come into play. They have been doing so for a long time. I mean, at a time when nobody knew what is actually happening, people were using colloidal gold, which is nanogold, for rheumatoid arthritis, and it is still in the market. So I think it happens with biomedical applications, the same things that happens with a lot of new technologies that should go into medicine. At the beginning, there is a completely new possibility what to do, a new technology. People are extremely excited. You have startup companies all over the place. All the companies want to be here. And then there is no quick payoff. And many of the attempts to create a new drug, they fail. This always happens. And then people start dropping the new technology. But some of the first attempts come through, are successful, and then it is taken up again at a reasonable rate and with reasonable expectations. So nanodrugs will not cure all cancers. I think we can be safe saying that, but they will contribute to a better management of cancers. We can also say that. So at the moment where we are in the phase where realism is taking place in the field. On nanobiotechnology, of course, we have other possibilities. There is a great deal done not with nanoparticles, but with nanostructured surfaces. Nanostructured surfaces play a great role. Implants would be a point here. If you have an implant for a bypass, or you get a stent, or you have an implant for fixing a tooth in your jaw, The surfaces are nanostructured now, and this gets more and more sophisticated because you need to suppress inflammation. And since nanostructures interact with the immune system, they could interact in such a way to really prevent inflammation. And a lot of attempts are done here, and a lot of good materials are already in the market. This is not counted as a drug, but a medical product, and it's cheaper to develop that because it's not so expensive to get approval. So there is now more good examples already in the market for bio-nano products for implants. There's the bio-nano can also go into biotechnology, where you combine nanotechnology and biotechnology for technical purposes to produce new products. I think here one of the areas where nano is really making a difference is in the field of green chemistry, where you are trying to stay away from toxic chemicals, toxic products, try to reduce energy consumption. And here nanotechnology is indeed a very hopeful contribution.
Okay, the last question is about the bottleneck. In your opinion, what is the bottleneck in the fields that you make your research?
The nanosafety research, yeah. The bottleneck is that we are good in the lab, but the transfer to the free world is really very, very difficult. It is not made easier by the fact that some of these many publications are not really suitable for risk assessment, because quite a number use high doses that are never reached in real life, and quite a number don't test appropriately for contaminations. In particular, bacterial compounds. Bacteria are everywhere. Humans carry bacteria. Your body contains 10 times as many bacterial cells as human ones. So we are full of bacteria, and this is perfectly natural. But bacterial products attached to nanoparticles stimulate the immune system. They create inflammation. So there is a lot of papers where you can bet that the inflammation reported was not the nanoparticle, but the contamination. Throwing out all that stuff is not so easy, and we are still in a process to focus the literature only on those papers that are suitable for risk assessment. Many of these papers have never been produced to say something about risk, but data are used today nevertheless. But the major bottleneck really is, I think, to go to industry. And we are trying to do that now. We are busy in projects. And here is also a function for industry. We need to link the scientists and the industry people. And the industry people need to tell us which type of data they need for safety. And they need to tell us which type of tests they can run. If we manage this together, we can end up with a set of tests that can be applied at those sites where nanomaterials are produced or handled or used for production of something. And then we would really be in a position to improve workplace safety. And at this point, from a human health perspective, certainly workplace safety is the key concern, and consumer safety less so, because only a very restricted selection of particles reaches consumers, and they are usually those that people have been working with a long time, so there's a lot of information. Well, in the workplace, you can really be exposed to very innovative and special materials.
Okay. I would like to tell you thank you so much for your interview. You contribute so much with our program. I know that what you tell for us, I can put more questions, but 1 hour, it's okay for us, and I hope he will have in the future new opportunities to discuss more this kind of research that you have been doing. Okay?
Yeah, thank you very much, and it was a pleasure talking with you.
Okay. Arline Arcuri will try to find you in the seminar in Porto Alegre.
Fine, I'm looking forward to it.
Okay, bye-bye.
Goodbye now.